Greetings, math fans. Alright, so today we're going to do a little bit more work on vectors. And the first thing I want to talk about is just a little notation. If I have v with a subscript of p, so v sub p, that represents a perpendicular vector to vector v, or orthogonal vector to just vector v. Okay, that's just v sub p. So real quickly, if I gave you vector v is equal to c comma d, what would a perpendicular vector look like? Well, what do you guys know? Don't you know that I need to multiply this by something and this by something, where that sum then equals 0, which is what? It's the dot product, right? So my v sub p, if I want to get that to be 0, isn't it going to be negative d comma c, right? Kind of opposites with the sign change. Because think about it. If I multiply that out, I get c times negative d plus d times c, which is negative cd plus cd, which is 0. Ooh, that's sweet. That works. Can you think of another one? Well, I just changed the sign of d. How if I change the sign of c? So can't I have d comma negative c? As long as the values are switched, the d and the c, I just need to change the sign of one of the values. So it can be either one of those two. Okay? And if it is, then we're looking at their orthogonal. Okay? All right. We already know the dot product. Okay? That was pretty easy, and we found out our directional angle is tangent of theta is equal to the y component over the x component, right? And we do inverse tangent, and we get that. And that gives us our reference angle, of course. Don't forget that. Here's an alternate definition for the dot product. So this is an alternate definition for the dot product. And it's equal to u dot v is equal to the magnitude, remember those bars mean magnitude of u times the magnitude of v. I'm not going to put a dot in there because it's going to get you confused. It's just u, magnitude of u times the magnitude of v times cosine of theta. And theta is the angle between the vectors u and v. Okay, that's actually pretty handy. It's really, really handy because you have two vectors. All right, if you have one vector, again, you're going to use our old form. One vector is, think about it, if you just have a vector a comma b, right? If I want to find the directional angle, I just do tangent of theta. It's one angle. All right, and then I do y over x, right? So I do b over a, and then I do the inverse tangent of that. Okay, so that's important. This is used for if I have two vectors. That's super important because the reason it's used for two vectors is because I've got my theta. That theta is the angle between those vectors. Okay, and by the way, that angle theta is going to be between 0 and 180 degrees. It's more than 180 degrees. Think about it. Here it's maybe 135, and here they're opposite vectors, so it's 180. And if it starts to come back around here, you don't add. It doesn't become more than 180. It's just actually less than 180, right? It goes back to like 135 or whatever. All right. So theta is between 0 and 180. And again, this is only if you have two vectors. Use this. If you have one vector, then you're going to use the inverse tangent of y over x. Okay, inverse tangent of theta equals y over x. Okay, very, very important to understand that. All right, so let's do a couple examples here. If you're given, and we have another word here called the norms, and the norms are another word for magnitudes. So if you're given the norms are 3, 8 of vectors u and v respectively, respectively means in order. So the U goes with the 3 and the V goes with the 8. And directional angle equals 20 degrees and 60 degrees, again respectively, which again the 20 degrees goes with the U and the 60 degrees goes with the V. I want you to find U dot V. Well, it's really easy. You just kind of plug it in, right? It's going to be U dot V is equal to the magnitude of U. Well, that's given. That's 3. Whoa, that's really easy. Times magnitude of V, which is 8, and it's times cosine of course, the difference between these angles. So theta is going to be 60 minus 20, which is 40 degrees. Pretty easy. Type that all in your calculator, and you get 18.4. And again, this is a scalar number, right? It's not a vector when you take the dot product. Make sure you are careful about that. Okay, cool. Let's do one where you have to find the angle now. All right, so here's your next example. I want you to find the angle between the given vectors. And your vectors are U is equal to negative 3 comma 2 and V is equal to 1 comma negative 4. Alright, so to find the angle we need to kind of fill everything else. First of all, we need U dot V. Okay, and that's easy. That's just going to be negative 3 times 1 plus 2 times negative 4. So it's negative 3 minus 8 is negative 11. Alright, and then I need the magnitudes. So the magnitude of U is equal to the square root of negative 3 squared, which is 9, plus 2 squared, which is 4. So that's the square root of 13. And the magnitude of V is equal to 1 squared, which is 1, 4, plus negative 4 squared, which is 16. So it's the square root of 17. So your U dot V, which is negative 11, is equal to square root of 13 times the square root of 17 times cosine of theta. And we divide both sides by square root of 13, square root of 17. Okay, so we get cosine of theta is approximately negative 0.74. Then we do the inverse cosine of that non-rounded value, and we get 137 degrees 44 minutes. That's your answer. That's the angle between those given vectors. Okay? Again, it's two vectors, so that's what you use. You use the alternate definition. If it was one vector, and I asked you just for the directional angle, tangent of theta equals y over x, the x. Okay? Not bad, not bad. Okay, so the next thing I want to talk about is I want you to determine if the vectors are parallel, orthogonal, or neither. Okay, of course, orthogonal being perpendicular. So here's the example. If you're given 4 negative 6 and 5 negative 15 halves. Well, the first thing is easy. Okay, the first thing I'm going to do is check if it's perpendicular. So you just do the dot product. So that's going to be 4 times 5 plus negative 6 times negative 15 halves. Well, I can see right away it's not. It's 20 plus 45, which is 65, which is of course not equal to 0, so it's not orthogonal. And this is the deal. To see if parallel this is what I'm going to do. I'm going to find a vector orthogonal to one vector, and then find the dot product with the other vector. So this is what I mean. If you have two vectors, what I'm going to do is you can't do a dot product for parallel. What I can do is I can find a vector perpendicular to this, right? And if I find a vector perpendicular to that, then what I do is I test this vector with this vector to see if that's perpendicular. Okay, so I find this vector that's perpendicular to this guy right here. And once I do that, then I see if that is perpendicular to this vector. All right, so this is kind of like a transversal here, and if these are the same, these are both right angles, all right, then I know that the original angles are parallel. Right? So let me just rewrite this now. Let's actually check that. So my original vectors were 4, -6, and 5, -15 halves. Okay, so I'm going to find a perpendicular vector to 4, -6, and you guys should be good with that, right? I just switched the values and changed the sign. So I'm going to make it 6, 4. That's going to be a perpendicular vector. And then I'm going to take that, since that's a perpendicular vector to 4, -6, now I'm going to do the dot product of that vector and the other original one. And again, if these are perpendicular, then the original ones were parallel. Well, let's do it. It's 6 times 5 plus 4 times -15 halves. Okay, that's a 2 and that's a 1. So we get 30 minus 30. Sweet. Sweet. So these are parallel. Okay? Now I want you guys to understand, if I give you just a single vector, so this is another vector here, so let me clear this off here. So this is another method. If I give you 5, 3, and I ask you to graph that, to sketch that vector, well, wouldn't you go 5 in the x for the x component and then 3 for the y component? And then here's your vector, right? And what do you know about that? I mean, you kind of know the slope of that line, don't you? Isn't the slope y over x? So it's 3/5. So really, if I look at, for any vector, I can look at the slope of that vector. And what do you know about slopes being parallel and perpendicular? Well, if we talk about slopes, if it's parallel, it's the same slope. And if it's perpendicular or orthogonal, it's opposite reciprocal slope. Okay? So that's really important. Same slope parallel and opposite reciprocal perpendicular. So let's go back to our original problem that we had. It was 4, -6 and 5, -15 halves. Well, let's just check out the slopes and see what they are. So it's almost like you don't have to even do the dot product, but once you understand about that, to do the dot product and the first method I showed you, but let's just check out the slopes. So isn't it y over x? So isn't it -6 over 4, which is -3 halves? Okay, so that's the first one. And what about this one? -15 halves over 5. Well, isn't that -15 tenths, which is -3 halves? Sweet! These are the same. So parallel. Okay? That's kind of a nice way to do it, actually, looking at the slopes. I think it's a pretty mellow way to do it. All right. Okay, so the last thing we're going to do here is writing vectors as linear combinations. Okay, so our first example is if I give you a vector I, which is going to be 1, 0. Well, first of all, what type of vector is that? You should recognize that as a unit vector because it has a magnitude of 1, right? And let's give you another vector j, and we'll call that one 0, 1, which is another unit vector. So these are 2 unit vectors. And what I want you to do is I want you to write -12, 105 as a linear combination of the unit vectors. So really this is what I want you to do, math fans. You're going to multiply something by the I vector, and then you're going to add that to multiplying by something times the j vector to give me the -12, 105 vector. All right, and this is pretty easy. So I'm going to actually write the word easy because it really is pretty easy, especially with a unit vector. Well, you multiply the first one by -12, right? And you multiply the second one by 105. Just think about it. Isn't that going to give me -12, 0 plus 0, 105? And if I add those vectors together, I get my original vector, -12, 105. So these are my coefficients, my scalar multiples, to get -12, 105. So it's truly -12 times vector I plus 105 times vector j. Okay, so this is really what I'm looking for. Those are my scalar multiples to get that. Let's do a little more complicated problem where it's not just a unit vector. So another example, I want you to write 15, 13 as a linear combination of 2 other vectors, 2, 3 and 5, -2. So basically what we need here, math fans, we need to have some value that you're going to multiply times 2, -3, and add that to some value that you're going to multiply by the vector 5, -2 to give me the vector 15, 13. All right? So we're looking for those coefficients, the coefficient A and B. So here's the deal. We're going to set up systems of equations. Okay, so set up a systems. And what it is you have your x components and you have your y components. So it's going to be 2a plus 5b, right? The x components equals 15. So again, these are my x components. And then we're going to do a y component. And that's going to be 3a and minus 2b. And that equals 13. And it's just a system, and you solve it. So I'm going to solve for b first, just because one's positive, one's negative. It looks a little easier. So I'll multiply this one by 2 and this one by 5. So we get 4a plus 10b equals 30. And 15a minus 10b equals 65. And if we add those together, let me just write on top here, we get 19a, the b's cancel, 19a equals 95. We divide by 19, so we get a is equal to 5. That's nice. And then just plug it into one of the equations. So let's plug it into the top one, doesn't really matter. So 2 times 5 plus 5b equals 15. So we subtract 10 from both sides, so we get 5b is equal to 5 and b is equal to 1. So there we go. We got a is 5 and b is 1. So now I can write this system, this is my answer, is I multiply 5, since 5 is my a, it's 5 times 2 comma 3 plus 1. That's kind of optional because it's just a coefficient of 1. We could just not even put a 1 there, but I'm going to put it there. 5 negative 2, and that equals our original vector, 15 comma 13. Okay? And you can even check it. So like I said, this is my answer right here. But of course you can check it just by multiplying it back out again. So it's 5 times 2, 3, which gives you 10 comma 15, plus 1 times 5 negative 2, which is 5 negative 2. So 10 plus 5 is 15, and 15 minus 2 is 13. Sweet. That's the same thing. All right? So that's what I mean by finding a linear combination, is find some coefficient in front of that the two vectors, some scalar multiple, to give me that vector that I'm looking for, the 15 comma 13. Okay? So that's it, math fans, for vectors, and I hope you learned something today, and I'll let you go. Adios, math fans. Goodbye.